everyone for coming to the first of the university lectures this year. It's my pleasure to introduce this year's university speakers, John Burkow. Before I give the introduction, I'd like to remind everyone about the other two lectures in the series, which will also occur at 4 o'clock here in Merker 127 on Thursday and Friday. And the posters are all over the department and also right here. So it should be an excellent 3 days of speaking. And I'm looking forward to learning and relearning some chemistry that I probably have forgotten. Professor Burkow was born in Cincinnati. We were just talking about his love for the Reds. And he moved to North Carolina when he was a teenager, and then went to North Carolina State where he obtained his BS in chemistry. He then went to Michigan to work for Hans Prinzinger, who was mentioned in yesterday's lecture, which was pretty fun. And he graduated in 1967 from NC State and 71 from Michigan. And then he went to Caltech, where he has been ever since. So since 1972. Oh, I apologize. Short stint. I apologize, John. 1971 to 1972, he was a postdoc at the University of Chicago with the great Jack Halpern. So seminal organometallic chemist. And then he joined the faculty at Caltech in 1972, where he's been since. John quickly rose to the ranks of full professor, and he became the Centennial Professor of Chemistry in 1993, which he still is that chair. And also recently became a joint professor at the King Fahd University of Petroleum and Minerals in Saudi Arabia. I think that just ended, though, correct? John's accomplishments are many, and I'm not going to spend a long time talking about them. I just wanted to mention some of the awards that are notable. He recently won the Gibbs Medal at Chicago and the Tolman Medal, which is a Southern California award. He's also won the Arthur C. Cope Award and the George Olah Award for hydrocarbons from the American Chemical Society. In the early 90s, John was elected to the American Academy of Arts and Sciences and also the National Academy of Arts and Sciences. John has many publications, and sometimes we talk about the number of publications, but I was thinking this morning about legacy and what legacy means. And really, I think the most impressive thing, in my opinion, about John's legacy is his students and postdocs. So John has had 61 PhDs and 51 postdocs. 25 of the PhDs are academics, and 27 of the postdocs are academics. That's 40% of people in John's lab. Either PhD or postdocs are academics. And I actually looked back at our picture from my last year, and we're about that ratio. The other 60% of people are no slouches on their own. I don't want to single out the academics. They are leaders in industry and very important people in industrial chemistry and also other fields. So when I think about John's work, there's a lot of things that come to mind. Many of the things that we learn in organometallic chemistry were brought about by Professor Burkow or hashed out by Professor Burkow. What is probably the most impressive thing to me, and the thing that drew me to being in John's group, was the combination of fundamental understanding of chemistry and its application to real-world problems. So John has done many things in fundamental organometallic chemistry, studying bond strengths, metal-carbon bond strengths, and also in applied organometallic chemistry with beautiful contributions in olefin polymerization and more recently olefin trimerization, both of which are multi-billion-dollar industries and in very important processes. Most of this chemistry is done with zirconium and scandium, and it's very sensitive, and I don't think John gets enough credit for this aspect, which I'm about ready to mention, and that is his synthetic capabilities. He has brought into light a lot of air-sensitive techniques that are difficult to do, but very beautiful and elegant. And so I have a swivel frit video, if you want to Google that I did with John's group, that demonstrates one of the most elegant ways to handle air-sensitive compounds. And so I think that that's a testament to John's synthetic capability and also his realization of innovation. So he's an innovator in terms of handling those kinds of compounds. In addition to the zirconium and scandium chemistry, however, he became a little bit more adventurous in the late 90s when he started a program in CH activation studying the Shilov chemistry, so CH activation of methane to methanol. And this led to lots of beautiful mechanistic works, as well as inspired, I think, a generation of people to think about CH bond activation and functionalization, which has become a very popular mode of bond activation in organic chemistry and also in inorganic chemistry as well. So without further ado, I'd like to introduce Professor Burka and welcome him to Boston College.
Okay, can you hear me in the back? Great. We need to switch something.
Oh,
here.
my fault.
Like that? Okay. Okay, well, thanks, Jeff. It's nice to be back. I think I was here about 15 years ago or so, my only other time to come to Boston. And I'm really pleased to come back and give these lectures because if I look at the list of distinguished predecessors who presented these lectures, it's quite a noble group, and I'm glad to be part of it. So today I'm going to start the first lecture by telling you about a very, very big project that's gone on for, gosh, 20 years or so. And I'm going to summarize it in about 2/3 of the talk. It won't be that fast, I hope. But then I'm going to give you something more recent that's relevant to the topic. And that has to do with trying to upgrade, as the VP sponsors call it, light hydrocarbons using oxidative routes to make something more valuable. Obviously, you're upgrading. Mainly transportation fuels is what they're after. Okay, so light alkanes, especially methane, are very prevalent, but they're really challenging, as you might guess, to do anything with because they're just simply not very reactive. You have carbon-hydrogen and carbon-carbon single bonds, and these are very strong and they don't react very readily. And we have a lot of this. This number keeps going up as we keep fracking and so forth, but there's a lot of it. Some people estimate that we have as much as 200 or 300 years of light hydrocarbons around to power the planet if we only use those. So even though we're thinking about solar energy and nuclear energy and such, we're still going to be using a lot of petrochemicals in the future and even into the moderate future, I guess. So we have a lot of it, but it's often not where we need it, so we have to transport it, and that involves very expensive pipelines, some of which we haven't constructed, like these red lines here, or liquefaction, which is what we're increasingly doing, making liquefied petroleum gas, LPG, putting it in these giant thermos bottles on ships and shipping it around and offloading it. I think there's something in Boston Harbor where you offload methane. It's sort of scary to think about. Don't want to think about a terrorist lobbing a grenade into one of these, I guess. But so there are political reasons that we have to overcome to use it for this. But of course, it's just expensive to liquefy methane. And in addition, we have light alkanes and alkenes that come out of refinery streams and various other processes that are simply not very useful in the way we do chemistry these days. And so often we sort of burn these things for their energy content in the refinery. It would be nice if we could convert them into something more useful like diesel fuel. So we do this. Clearly, we are capable of doing all of these transformations I'm going to talk about. But the way in which we do these upgradings is currently very energy intensive. It takes a lot of energy from other methane And a lot of them therefore produce a lot of carbon dioxide and certainly wouldn't be called green. So this introduces the topic, we need new catalytic reactions that will take methane and alkanes to liquid fuels. So how do we do it currently? We do it indirectly. We take methane, for example, or white alkanes, or coal, or biomass, and we heat it with steam over a nickel catalyst, and we can make this CO hydrogen mixture called Ssing gas, and we do this on an incredible scale each year. But the problem with this chemistry is that this is uphill, 50 kcals per mole almost, or each enthalpically uphill. So you have to heat this to these tremendously high temperatures in order to drive this reaction. At these high temperatures is downhill. You still need a catalyst, nickel catalyst, to do this. But once you do it, you have syngas, and as the name suggests, we make lots of molecules from syngas. Essentially, all of the methanol we make is made from syngas. We do what's called Fischer-Tropsch synthesis to water and other hydrocarbons. And we water gas shift the CO hydrogen mixture to pure hydrogen and CO2, which we separate, and that hydrogen is used to make ammonia on also very large scale. So these are very, very large volume processes that are practiced. But the thing you should take away from this slide is that red number, very high uphill, and this picture of a steam reformer where the action's going on here with a nickel catalyst, and these flames are ripping down along the reactor there to heat it up to the temperatures required to drive this reaction. So we want to avoid this. So what can we do with direct methane strategies? And it's always useful to think about thermodynamics before you start thinking too far down the road. You want to avoid this thing that's now in gray. There are direct reactions you can envision, like inserting a carbon monoxide into a methane CH bond to make acetyldehyde directly rather than indirectly. But this is also uphill. It's not too bad. CO2 to acetic acid, more uphill. Downhill reactions are methane plus ethylene, for example, to make propane. That's downhill, but don't go to an energy company and tell them you have a catalyst that will do this, because they will laugh at you, because ethylene is the primo petrochemical for making all kinds of things, much more valuable than propane. And so you wouldn't like to take methane to propane, even though it is downhill, unless you're an academic and you like to do unusual reactions like inserting olefins into CH bonds. But we're talking big volume here. So what are direct routes that are favorable thermodynamically? And essentially all of them are partial oxidations. Of course, you can take methane and oxygen and cleanly make CO2 and water. That's what we do when we get energy out of methane. And that is the most downhill. That's 50 kcals per mole downhill. But if you can make methanol directly, it's downhill. You just need to stop before you go all the way to carbon oxygens and water, carbon oxides and water. And so we need to find a catalyst that will do this. There are some catalysts that do things related to this, like methane monooxygenase. This would be a dioxygenase. You don't have to make a bowl of water for every methanol in this reaction, like methane monooxygenase does. But so there is a hope that we can find some kind of a catalyst that will do this in a selective way. Oxidative coupling to higher alkanes would be a way toward diesel fuel. In each of these steps that makes a molecule of water is very downhill. And so again, this is something that looks attractive, but I'll tell you that there's no catalyst, none that will do this with sufficient selectivity and high conversion. And as long as we're dreaming, take methane and make ethylene. As far as I know, there's no catalyst for this, although there are some claims in the patent literature and in the popular literature that I think the company's called Soluria is building a pilot plant to do this, but there's, so far as I know, no details about yield and conversion and so forth. But if you can do this, this would be a really nice reaction. So this has been known for a long time that these are downhill and these are very desirable. Why can't we practice these yet? And the answer is that it's hard to do this with sufficient selectivity at high conversion. If you're willing to stop at about 5% conversion, there are some catalysts that will do this, but that's prohibitive in terms of practicing it on a big scale. And the reason is that we're plagued with this odd oxidation mechanism I'll show you in just a minute. And as long as we're talking about partial oxidations, it would be wonderful if we could make olefins from like hydrocarbons, like ethane and propane and naphtha in general, by some process other than what we do now. We do what's called steam cracking. That is, we dilute these hydrocarbons with lots of water, and then we heat it to a tremendously high temperature and low pressure, and that cracks these into these olefins with reasonable yields. This is very well developed chemistry, but we have to heat all of these up to over 1,000 degrees, and we have to dilute it and heat all that water, all that steam, because if you don't, these give lots of carbon, and once you get the molecules diluted with something, and steam seems to be something inert enough to allow you to make these with good yield. And so again, these are very endothermic processes. These are very big investments, over $1 billion for steam cracker. And it would be wonderful if we could just partially oxidize ethane to ethylene. This is downhill. We just need a catalyst that will do it. But again, we haven't found one because of odd oxidation. And odd oxidation is a process that involves pulling hydrogen atoms off of the carbon substrate by some sort of very reactive oxygen species. And here I show in brackets with an oxygen in the center. This homolyzes CH bond, giving, in this case, an OH radical and a methyl radical that you could hope could get together to make methanol. If that happened, you now have a product whose CH bonds are much weaker, 10 kcals per mole weaker than those of methane. And if these are homolytic reactions, you might guess, and you would be right, that the rates of abstraction of a hydrogen atom from another atom will correlate with the strength of that heteroatom hydrogen bond. So the stronger bonds are going to be less reactive. The weaker one's more reactive, and that's the problem you cascade down to formaldehyde, formic acid, CO, CO2, because these get faster as you start adding oxygens to the carbon because you weaken the bonds. It's not quite so bad if you think about coupling strategies. The CH bonds decrease in strength more slowly, but it's still a problem. And no one has figured out how to do either of these processes because these radicals react. These radical type processes correlate, their relative rates correlate with CH bond strength. And this is the devil that's always sort of waiting in the wings for any kind of strategy you can think about for taking hydrocarbons and partially oxidizing them. Because even if I invent some magic catalyst that does it beautifully, if an odd oxidation mechanism ever kicks in, it's going to probably dominate the process and you'll have a flame, essentially, instead of what you want to happen. So this is something to keep in mind when people like I talk about these things, that this is a very big barrier to overcome. I'm an organic transition biochemist, and over the many years of my career, I watched organometallic chemists devise ways to activate, as we call it, CH bonds, that is, break the CH bond, by processes that don't involve these things like oxygen, reactive oxygen species homolyzing them. Most of them involve oxidative addition, and we know how to do this even at very low temperatures, and we know how to do it even on methane. Very cool. We can do it in a non-redox way with this process called signal bond metathesis. And again, methane is a substrate that will do this reaction. And you can add the CH bond across a multiple bond, usually a nitrogen metal double bond, to make an alkyl and that bond. And you can do it in a radical way by taking two sterically encumbered metal-centered radicals and prying apart the CH bond to make, for example, a methyl species and a metal hydride, again, at really low temperatures. The problem is coupling these kinds of fundamental steps that activate CH bonds with an oxidation process, especially one that makes water or an alcohol product. So an oxidation process, then, especially one that uses dioxygen directly, is not going to work here because you can imagine that if a metal is oxidized by a CH bond, it will react more rapidly with dioxygen. And that's true here of the metal radicals as well. And these processes that don't involve a formal redox of the metal don't tolerate oxygen products like water and alcohols because they react selectively with them. Because these are generally early transition elements or lanthanoids that make very stable hydroxides or alkoxide products. So you can imagine coupling these. But there is one way in which you can activate CH bonds that seem to be different. It's got various names. I call it the electrophilic displacement of a proton. And many metals will do this, not only transition elements, but metals like mercury 2 or thallium and so forth. Ions will react with CH bonds to release a proton and make a metal alkyl. And many years ago, Jay Lebinger and I thought about how we might do this partial oxidation chemistry, and we decided to take a look at this electrophilic method. And there was already, when we started on this, a long-standing report from Alex Shillop. This is a picture I took of Alex 25 years ago at least. And Alex describes some chemistry. By the way, Alex passed away in August of last year. He was a very distinct Russian chemist. And he had a claim that you could take methane in water and add platinum halides and get an incredible reaction. The methane was converted to methanol, and you got HCl if you used platinum halides. And you just had to heat it to about 120 degrees. You had to have a mixture of platinum 4 and platinum 2 for this to work. You started with very pure platinum 4 with no reaction. You started with platinum 2, other things happened that weren't as nice, precipitation of platinum metal and so forth. But this stayed homogeneous if you used a large amount of platinum 4 and a little bit of platinum 2. Alex reported many features of this, and we went back and repeated this chemistry and convinced ourselves it was true. It turns out to be catalytic in platinum 2, but stoichiometric in platinum 4. So this is the oxidant. We're not using dioxygen. The oxygen atom comes from water. But it's a very crazy reaction. The oxidant is reduced to the catalyst. And chloride is a strong inhibitor, so it has crazy kinetics. We could never get it to work out in a way that we could decipher from kinetic analysis, because there's also a complication that it is at reasonable conversion, like 80%. The platinum 2 started serving as the oxidant as well as the catalyst, and that means you start getting platinum deposition. And the minute you get platinum 0, there's a presumably heterogeneous process that goes on that takes methanol on CO2 and water. But, and I should point out that if you add dioxygen, it's not incorporated, at least in this version. It doesn't serve as the oxidant, the stoichiometric oxidant. But the good news is it doesn't stop the chemistry. It still goes on, even if dioxygen's around. So this is a water and dioxygen tolerant catalytic conversion that we thought warranted more exploration. It has very unusual regiochemistry. Primary bonds, strongest ones, are much more reactive than tertiary ones. That has this unnatural order of reactivity of various kinds of CH bonds, including the fact that the methanol product is only of comparable reactivity to the methane starting material, and amazingly, the alcohol is not, at least in some cases, further oxidized onto the aldehyde or the carboxylic acid, which is a much easier oxidation with normal oxidants that we use in the synthetic laboratory. So how does it work? So this is the bottom line slide. I'm going to give it to you early and then give you some evidence we have for the various steps in it. It occurs, as Alex Shillop suggested it did, by 3 steps, 3 stages. The first step is an electrophilic attack, as we saw earlier. This is an electrophilic CH activation. And so the platinum-2 electrophile, we just got some mixture of chloride and water ligands on it. We don't think it's all water or all chlorides because those are things that do not react with methane. But if you add a little chloride to the aqua, you get this chemistry to start. So here's what Alex thinks is reactive species, and I can't disagree. But in any case, some platinum-2 species spits out a proton when it reacts with methane and gives a platinum-2 methyl. And interestingly, this reaction is uphill slightly. So if you make this independently and expose it to a proton, it will spontaneously go into methane and platinum-2. So this reaction is reversible and uphill, and nothing would happen if there weren't an oxidant. And the oxidant is platinum-4. It intercepts this platinum-2 methyl species and oxidizes it up to a platinum-4 methyl species. But that completely changes the reactivity of the platinum-methyl bond. Whereas this is a methyl group that's susceptible to protonylysis, this is stable, even in 10th molar acid, to protonation. But it does react with nucleophiles like chloride or water and spits out products, methyl chloride or methanol. We have looked at the mechanism of these last two steps in some detail, including an isotope study where we bought $1,000 worth of platinum-195 enriched platinum. It has a spin of 1/2, so it's a nice NMR probe. We got 1 gram for that, by the way. And we dissolved that little bit of platinum wire in aqua regia and made platinum-195 enriched hexachloroplatinate and used natural platinum-2. And we got natural platinum-4 methyl as the initial product. So this is electron transfer. It's not methide transfer to platinum-4 in the oxidation study. That's the good news because we might now think about using some other oxidant that could serve the role of this very expensive oxidant in the original Shillop cycle. I should point out to you that you need to be careful in your choice of oxidants. You want to wait until this first step has occurred before you oxidize the platinum-2 up to 4. And nature's working with us here because if you make platinum methyl bond, you make this platinum-2 more electron rich. This methyl group is very electron dominating, and the potential for oxidizing this is higher. Of course, in this case, it's almost a degenerate oxidation. And that's probably why Shillop found it with that oxidant to start with, platinum-4. In fact, we found that copper-2 chloride will intercept this. And in fact, it does it even more rapidly than platinum-4. So this first step is uphill slightly, and it still amazes me that the reverse, just simple protonation, can be outcompeted by platinum-4. And at 120 degrees, this is favored by about 2 orders of magnitude by molecular rate transfer. So this oxidation step is amazingly fast. Now the last step is an SN2 displacement. It's not a reductive elimination of methyl chloride. A ligand has to come off of platinum-4, we think, and then there's a backside attack on the methyl group to make either methyl chloride or methanol. And we did establish that with methyl, but with other partially deuterated alkyl groups, that this goes within clean inversion of stereochemistry of carbon. There you guess for an SN2 reaction. So this SN2 reaction places these pair of electrons on the platinum and makes 3 forms of platinum-2 and goes around the cycle here. But what we need to do, if I can say it in a very good way, is find a way to get dioxygen to do this oxidation. And then we have a catalytic version that might be actually useful. But the first step I haven't talked very much about, and this is the most interesting step to me. It's the most frustrating to study, but it is the one that determines the relative rates of the reactions with various CH bonds and the selectivity, therefore. We tried, as I said, to do kinetics on the Shillop system and get at this rate determining step here, but we were unsuccessful. So we wanted to know what are the elementary steps that comprise this overall reaction. This is not an elementary step. It involves lots of things like water cleavage and CH bond cleavage and somehow losing a and so forth. So there are many elementary steps, as I'll show you along this path. We wanted to know what they were. So we did something we were forced to do, but I do with caution, and I caution you. If you can't look at the real system, you can look at a model system, one that is more stable and more amenable to clean mechanistic work. And that's what we did by stabilizing the platinum with ligands other than waters and chlorides. But then you have to be careful that that has some relevance to the real shell-out chemistry. We have convinced ourselves that that's true. So I'm going to tell you about model chemistry now. And some of the system that we settled on, although we found some others earlier on, were inspired by Max Tilsit's group in Oslo. And he sent Lars Johansen to Caltech to learn how to do a mechanistic study of this reaction that they discovered there. Working in trifluoroethanol with a platinum dimethyl stabilized by this diimine ligand, you're able to protonate off cleanly one methyl group as methane, and one of the solvent molecules, trifluoroethanol, coordinates to the platinum 2 cation that's left behind. You have this strange counter-anion that seems to be innocent. But this chemistry is very interesting because this platinum methyl cation, this platinum 2 methyl cation, with a trifluoroethanol coordinated, is reactive towards CH bonds, like that of benzene, and it does a very clean transformation to make a platinum 2 phenyl species with liberation of the second methane. So here I am wanting to activate methane, I'm making methane in the stoichiometric reaction, but let's not think too deeply about that. This is clean, so let's study it. That's remarkable at the outset because we work normally in anamorphic solvent, so we work at great expense with per-deuterated trifluoroethanol. And we can see that even with stoichiometric amounts of benzene, there is no deuteromethane formed. So even though you have a large number of CH bonds in the solvent, they're totally unreactive. Somehow this CF3 group and perhaps this hydroxyl group on that carbon deactivates those CH bonds. Essentially total as far as we can tell. So we have studied the mechanism of this and substituted arenes and various aryl groups on our diimine ligand in great detail. And the bottom line from all of these studies is that this chemistry proceeds in sterics through association of arene through the pi bond to the platinum 2 electrophile. That's certainly what you should think of if you're a chemist and you think about, where the electron energies are, these orbital energies are. The pi bond is certainly more basic, and so an electrophile would be expected to coordinate to the pi bond. We can actually see this A2 arene benzene complex, as I showed here, by protonating the methyl phenyl compound and running backwards to this at low temperature. We can see this. We think this slips from the pi bond to the sigma bond of benzene to give this sigma atom, and then this oxidatively cleaves to the phenyl hydride methyl cation, and it goes back. And these oxidative cleavage reductive coupling processes are very rapid, including the one that gives the methane sigma atom, and that then is displaced in a relatively slow step compared to these processes by trifluoroethanol solvent to make methane. So here's the second amazing thing to me at the time, anyway, I guess we're more comfortable with it now. And that is, you would think if you reductively couple to make this methane sigma atom, the game would be over, the methane would be away from the model and it would all be complete. But this, and I'll show you other chemistry, argues strongly that it goes back and forth between the methane sigma atom and the methyl hydride many times before TFE eventually associatively displaces that CH bond. So this CH interaction with the electrophile has some energy associated with it that makes it kinetically significant. Okay, so there's benzene. What about methane? This is a lot harder. First you have to do a isotopic labeling study because you're going to make methane when you activate methane. But that's pretty easy. But it turned out to be difficult to run in the forward direction. So we did something that mechanistic chemists often do, and that is we looked at the microscopic reverse of the process. So we, we want to know how does methane react with this methyl TFP catamaran to get into this box, this manifold reactions. And so we approached it the other way. We got into this box by protonating the dimethyl compound. We did it with D+. And when we put D+ on platinum 4 and looked at the product mixture, it was interesting when it went this direction, down a little way, that we got essentially a statistical mixture of two sets of products. One was the all-proteome methyl and deuteromethane, which is what you might expect. But we got 3/7 of the product had the deuterium on the methyl group that was left on platinum, and we got CH4. And that is a very revealing observation because that requires that what you get here, you reductively couple to the methane sigma adduct, you rotate from CD to CH. Computations and other experiments show that's a relatively low energy rotation. In fact, some of these sigma addicts involve 2 hydrogens in the platinum that are about the same energy, so that's a very shallow reaction profile. And once it slips over there, then it can oxidatively cleave the other way and reductively couple in the opposite way and eventually lead to the odd product, the one that has deuterium and the methyl group left on platinum. So the fact that it's almost statistical requires that all of these reactions in the box be fast relative to the associative displacement of the methane from the platinum sigma methane atom. And so that's also interesting because that requires, by microscopic reversibility, that the way you get into the box in the opposite direction is the associative displacement of the solvent, TFE, by the methane CH bond. So the way in which these things react is by a slow sigma bond coordination and displacement of the solvent molecule. That's why TFE is so special, is it binds so weakly to this platinum electrophile. We've looked at higher alkanes, not very many, but some of them. We looked at cyclic alkanes like cyclohexane early on, because they have all the same kinds of CH bonds. And we have looked at these reactions, and the deuterium kinetic isotope effect is normal, greater than 1, but not very much larger than 1, only 1.3. That's consistent with coordination, weakening of the CH bond by coordination, but not full breaking of the CH bond on reaction with cyclohexane. And then we find a different product. We don't stop at the methyl or phenyl. We have beta hydrogens in this product, and so we get the cyclohexene will hydride cleanly. So these reactions are quite clean. We've looked at other cycloalkanes. We've looked at normal alkanes and methane, even using high pressure NMR techniques to get that number. And these are the second order reaction rate constants for all of those substrates. All of them, we think, involve CH bond displacing the solvent molecule. And if you normalize them for CH bond of the substrate, cyclic alkanes are identical. The normal alkanes are, of course, have primary and secondary CH bonds. And I don't know what to make of how these things go down. It suggests that maybe the primary bonds are slightly more reactive than the secondary ones because relatively more primary you have relative to secondary, the faster the rate constant. But they're not very different either. Let's look at that. And that's a factor of 2 for most of them. And interestingly, methane is relatively slow, still comparable, but slower. And you can argue about that. You can argue about these also. People like me say things like, this must be some sort of steric and conformational effect that's going on here. When you hear people like me say that, you can just conclude, he doesn't know what's going on. Don't even think about it too hard. We don't know either. But why is methane slower? It is the smallest. So you might guess, just on steric grounds, it would be the best nucleophile. Think of methane as a nucleophile for a CH bond. But it also has the strongest CH bond to break. So it's going to, even though it's only weakening in our coordination, it still starts out very strong. it should be slower. And furthermore, if you just think about how electron-rich that CH bond is, it only has, of course, 3 other hydrogens on the carbon, rather than another carbon that might pump up the electron density and make it a little bit better ligand for platinum-2. But whatever the true reason, it's not very different. And the bottom line from this study is that if you're a CH bond, you're going to have an alkane, you're going to have about the same reactivity as another alkane CH bond. And maybe that sounds terrible. There's no selectivity for alkane CH bonds, but in terms of oxidation, that's a lot better. We're not talking about orders of magnitude difference like we see for tertiary, orders of magnitude more reactivity for CH bonds on the tertiary carbon versus something like methane. Okay, so how does this go? I've already suggested it. Let's get on with it. We think it goes by this rate determinant coordination, and then the oxidative cleavage, reductive coupling business goes on in the productive way or back where you were, and eventually solvent-assisted displacement of the methane occurs. So the study of this first step concludes that the rate-limiting step involves the CH bond getting on the platinum tube. In the Shillog chemistry or not. In this model chemistry, certainly, and by extension, the Shillog chemistry. Okay. And we have looked also at alcohols and other kinds of substrates like ethers that have heteroatoms on the carbon CH bond, and looked at the Shillog chemistry too, and we get comparable differences in rate for those, but they're not very different. What about a catalytic version? I told you that copper-2 is capable of carrying out the second step, the oxidation of the platinum-2 alkyl to the platinum-4 alkyl. We extended on some earlier reports by Ssing and his group and State, and used copper-2 in combination with dioxygen to carry out the oxidation. So the ultimate oxidation occurs by dioxygen reduction. And the copper-1 product from the platinum-2 oxidation is reoxidized in copper chloride with copper chloride to cupric chloride in solution. And this chemistry we did in water, these water-soluble CH substrates, amazingly selective. In all cases, this sulfonate group deactivates the CH bonds next to it, but the methyl group, and it's more reactive. And we get exclusive alcohol or chloride at that beta position in these oxidations. And indeed, it works. You can do tens of turnovers. We did this work at Los Alamos in a pressure reactor that they have that's safe there. And we did it at high temperature and high oxygen pressures to get as much as 100 turnovers in the best cases. And once again, we see this selectivity for making benzyl alcohol, a little bit of aldehyde in this case. But this chemistry is capable of being catalytic. But I mean, the problem is it's not practical. The catalyst eventually dies in this case. And it's interesting that the cupric chloride will not react with what I call the inorganic platinum to the catalyst, the one with chloride and water ligands on it. It presumably reacts with the platinum too, although that's very fast. But when we get through and the catalyst is dead and we look, it's not platinum metal, it's platinum-4. Hexachloroplatinate is formed as the inner final material, and whereas this doesn't react with platinum to make platinum-4. We think something in the reoxidation, perhaps peroxide or something, is generated that does do the oxidation of the inorganic platinum-2 up to platinum-4, and that's what ultimately kills it. So this probably warrants going back and looking more carefully at. But that's sort of the best case that we've come up with so far. So let me stop this discussion and conclude that with the prospects for it. The best system so far that we've found is not a model system, platinum 2. I guess I'm getting to be famous for a statement of observation that I make, and that is that the best system is always the first system you discover, and then when you make changes in it, very rational changes, it just gets worse. And that's a very pessimistic, fortunately not always true statement, but I'm afraid it's true more than we want to know. In any case, this is one of them. And I've gone through this, these bullets here, and I'll just quickly state that these are very different kinds of reactions and oxidations. They don't involve radical intermediates. And there's a rate-limiting sigma adduct formation. That is the rate determining step. And these are just simply too slow for anybody to practice. The original oxidation system with platinum fluoride is prohibited, of course. And even this catalyst system with copper and dioxygen that gives up to about 100 turnovers is too slow and has too short a lifetime. If we're going to have any kind of practical application of this chemistry, it's going to have to be in a flow reactor. Nobody wants to make methanol in water and then have to separate it, and that's too expensive. So you need some kind of a flow system. And so this is sort of where we stand. I should point out something that I guess Jeff was getting at, and that is that there's a lot of variations on this chemistry that involves CH activations and functionalizations in the synthetic organic community, especially where CH bonds now are functional groups. If you use this kind of chemistry that's related to the Shaw chemistry, they use very expensive, prohibitively expensive for big commodity chemical or fuel application like hypervalent iodine, boranes, or even olefins to oxidize these intermediates, not dioxygen. This work has been supported by BP for now 15 years, and they're still supporting this kind of work in my group. But even after about year 7, it was clear that we weren't going to have a big breakthrough in this methane oxidation chemistry. I applaud BP. They didn't just say, too bad, you didn't find a solution, so we're cutting off your funding, go do something else. They encouraged us to look more at alternate strategies, the indirect strategies. And what do I mean by that? Well, we're back to this slide, where you have to do syngas chemistry. And we were interested in maybe making a homogeneous analog to this Fischer-Tropsch process and doing syngas chemistry. Because this is a funnel point, as I suggested, for all kinds of biomass, coal, methane, white alkane feedstocks. And in fact, this Fischer-Tropsch process is being looked at very seriously by all the energy companies. It involves CO and hydrogen reacting much like ammonia synthesis to make hydrocarbons in water. Depending on the catalyst, iron, cobalt, you get a different product stream. But it's essentially a polymerization process, oligomerization process more appropriately. And so you get a Schultz-Flory distribution of products, although methane is always formed in higher yields than that distribution predicts. But you do get a mixture of things. You can vary the cut that you want to make anything like gasoline or diesel fuel. But it's essentially crude oil that you're getting out of here, and so it has to go into a refinery. But as I said, people are interested in this. We have done some work, I'm going to talk about, on syngas chemistry, trying to find a more selective variant. And we've done some fundamental work in that area, but we're not able to beat the Fischer-Tropsch system yet. I'm going to talk briefly about an alternative, and that is to use light hydrocarbons, not just methane, but light hydrocarbons, and some sort of way to upgrade them. And as I suggested in the beginning, we have a lot of these. They're produced not only in ethane and propane or minor components of natural gas, but they're also byproducts of catalytic cracking in the refinery. And if you're going to practice Fischer-Tropsch, you're going to get light hydrocarbons, mainly alkanes, but also alkane-alkene mixtures. And we would much rather have transportation fuels. And so we are thinking, as others are, about how you can take those hydrocarbons, like alkanes and alkenes, and somehow get them coupled in a selective way to make products that are more useful. And the first process that I think got a lot of attention is one that mainly Maurice Brookhart and Alan Goldman have developed in combination with people like Dick Schrock and others. But early earlier work by Ssing involved this so-called alkane metathesis process. And this involves tandem catalysis, two catalysts, one that takes hydrogens off and puts them back on, the alkane fraction, and then this alkene that you generate is subjected to a olefin metathesis catalyst. If you do the simplest one-step way to do that, you make ethylene and higher alkene, and then the hydrogen catalyst, hydrogen transfer catalyst, will put the hydrogens back on to make, in this case, decane and ethane from hexane, two hexanes. This process works. The ideal reaction is almost perfect. You don't necessarily want this propane byproduct. But there are some disadvantages that were discovered, not surprisingly. The catalysts that do olefin metathesis, and even the hydrogenation transfer catalyst, can isomerize the olefin and then do secondary metathesis reactions and so forth. And this gives you a very non-selective product mix due to this alkene isomerization byproduct reaction. And you do lose ethane for everything that you do in a fuel reaction. The two catalysts they used are this familiar class of so-called iridium pincer ligands that do the transfer hydrogenation. And the best system was the Schrock system for doing the metathesis step. And that same system uses a supported alum hydride catalyst. That's a very good idea in principle, because I said we need supported catalysts to do this kind of big scale kind of chemistry. It's not very selective, and the rates are very low compared to what we really need. So we thought of a complementary strategy that we've been looking at more carefully. And that is to take advantage of the fact that a lot of times you have alkene mixtures, and it would be good to somehow couple those two together in a selective fashion. And so our thinking was that we would take the alkene fraction and we would make a dimer. I show you here a dimer that we've been making with our particular dimerization catalyst. This tail coupled product, this gem substituted olefin. And then you'd have a second step where you use your transfer hydrogenation catalyst that would take the two hydrogens from the alkane fraction of the feedstock, put them on this dimer, and make this higher alkane and more alkene that would couple with more of the starting alkene to make more of the dimer and so forth. So this could, in principle, run in a flow system with a constant feed of substrate mixture. And the net reaction is effectively hydroalkylation of the alkene by the alkane, where we've added the alkyl and a hydrogen across double bond of the alkene fraction. This is, of course, two molecules going to one, and so there is an entropic barrier that you need to surmount. This is enthalpically downhill, and we've done some calculations that suggest this is thermodynamically favored as long as you're below about 250 degrees centigrade before the T delta S term kills you and goes the other way spontaneously. There are always challenges in tandem catalysis, and those have to do with finding two catalysts that have to operate together that don't react with each other. Many alkene dimerization or oligomerization catalysts are known, but most of them involve very harsh activators like Lewis or Bronsted acids, high temperatures, and they're commonly not very stable. The transfer hydrogenation catalysts, by contrast, are deactivated by these kinds of activators for the alkene activator part of it, and they operate at relatively high temperatures. So finding things that are compatible is difficult. And to illustrate that, if you try to use one of the Grubbs catalysts for the olefin metathesis step in the Goldman-Brookhart chemistry, you will find that it's not possible because the chloride is transferred from the ruthenium to the iridium, and neither of those byproducts are stable. So Dave Leach, who was a postdoc in the group who tackled this problem a few years back, looked through the literature and found this very interesting catalyst that Dick Schrock was working with back in the early 80s with Steve McLean, one of his graduate students, the CP star tantalum dichloroethylene. This is by itself, with no activator, and very selective alkene dimerization catalyst. It only works on one alkenes, not on internal alkenes. Dick, in his own sort of exaggerated natural style, said it was indefinitely active. He's almost right, it does decompose eventually. I guess that. But it is amazingly stable at 150 degrees. And so that was our choice. And our transfer hydrogenation catalyst choices were a lot narrower, and so we chose this iridium pincer-ring system. Very well studied, and it will selectively convert N alkanes to alkenes if you have the right ligand system. So our initial idea was to probe this possibility that we could carry out this tandem catalytic sequence. And so we looked at liquid feedstocks. And these would give a diesel length product, and so BP was happy that we were working on this. So we looked at we first saw whether both catalysts worked or not, independent of one another. And catalyst A made dimer, as you might guess, C12 dimers, and we got about a 3-to-1 mixture of these two at the tail couple products. And when we probed the combination of the catalyst, we decided to use a hexene substrate and heptane solvent. So we got the desired chemistry. We would get, in addition to C12 dimers, we would get C13 products and C14 products from the heptane that was generated by transfer hydrogenation to the hexene to make hexane. Okay, so we tried it. We tried it with this so-called Pocock catalyst for iridium, and we did see that chemistry occurred. We got dimers, we got hexane, so we were somehow pulling hydrogens off heptane, but we didn't see any heptene incorporation in our olefin products. And we think that's because this particular iridium catalyst pulls off hydrogens or makes internal alkenes very readily. And so even though we were pulling hydrogens off here, we weren't getting a terminal alkene. And this tantalum catalyst is very selective for having a terminal alkene. So we varied it, and we found if we used this T-butyl substituted chelating phosphate aerial system, this worked amazingly well. We heated this up to about 125 degrees, and even in our initial experiments, we got significant amounts of C13 products, amazingly, comparable amounts of C14 product dimers, in addition to hexane and some internal hexenes, and of course the C12 dimers. And we got turnover even in this first experiment, so this was amazing that our first or second try really worked so well. We have this cooperation factor that we talk about. How much of the hexene that's generated by the iridium catalyst transferring heptane solvent and transferring it to the hexene is incorporated into the C13 or C14 products. That would be cooperativity, where the tantalum picks off the heptene and couples it with hexene or itself. This is not the catalytic cycle we were after. We were interested, of course, in making the saturated dimer, but we weren't getting reaction of the saturated dimer, and that turned out to be a real bottleneck in closing the catalytic cycle. But we were doing hydroalkylation of this alkene. Although we made an alkene product in this case. All right. So we optimize this catalyst cooperativity number by varying temperature and so forth. And to our measurement, although this iridium catalyst normally works at 150 to 200 degrees in the systems that Schrock and Goldman were, that Ruckhardt and Goldman were looking at, we found we could go as low as 100 degrees. In fact, 100 degrees worked better than even higher temperatures. So this seems to be very cooperative. And we got numbers around, bouncing around about 50% or so. we found that if we slowly added the hexene to the heptane solvent to keep the hexene concentration low, naturally we would expect to get less of the unproductive dimerization of the hexene relative to hydrogenation from the heptane. And so the cooperation number could go up. If we added it over many hours, we got cooperativities of over 90%. So this chemistry is working pretty well. I don't have time to take you through all of this work. If you want to know about how the dimerization cycle works and how the iridium cycle works, check out this very big paper in Catalytic. But we got lots of information on this cycle that Schrock and McLean had looked at under conditions at much lower temperatures. And there are different resting states, and so there are different features of this tantalum chemistry than the earlier analysis revealed. The iridium chemistry worked out mainly by Brookhart and Goldman, and we find much of the same features. But in terms of carrying it out in a tandem fashion, there are two competing processes that we are seeing in our chemistry. There's a competing desirable step where we transfer hydrogens between the alkane and the alkene, and the undesirable thing that involves isomerization of the alkene to make the unreactive internal olefins. We've looked at the temperature effects on these relative rates, compared them to the dimerization effect, temperature effects, and I would just give you the bottom line here. These two catalysts they are cooperative, they will work together, but they have very different alkene concentration effects and very different temperature effects. The tantalum system sits in this monoolefin state under the reaction conditions, and so there's a positive order in one alkene when we are looking at the dimerization part of the tantalum catalysis. And in the iridium transfer hydrogenation step, it's sitting in the alkene form, and you got to get the olefin off in order to do this. So there's an opposite order, inverse order in alkene here. So these are working against each other. And those same sorts of pre-equilibria work against you temperature-wise too. The iridium chemistry goes much faster with higher temperature. The tantalum chemistry, of course, because we got to get an olefin on it, doesn't go much faster as you raise the temperature. And so these two things, although they're working together, are not ideally suited. So here we are. We're stopped at this stage, and we can't find a system that will transfer hydrogens from our linear alkene to our anti-substituted olefin, only to the terminal olefin do we see alkene transfer. And so going forward, we're going to have to find a dimerization catalyst that gives us more linear alkenes. It doesn't even have to be the terminal alkene. If we can chase this double bond up and down the straight chain here, we can get enough one alkene in principle we dimerize and complete the cycle to make straight chain alkanes. And we're trying to do that in collaboration with the Davis group using solid mesoporous zinc catalyst that has a nickel catalyst in it. So we're working on that supported strategy at this point. I'll conclude by saying, and talking about both of these sections up the top today, that we're interested in, of course, making upgraded products from light alkanes and alkenes. And there are some promising leads that we've come up with. But as I say, none of these processes are ready for prime time. The catalyst stability, and I keep emphasizing this, the process scale that's required for any kind of impact on what we're doing already is just an enormous barrier, as is the natural inertia and infrastructure barriers that industry has whenever you talk about changing processes from what they're doing. So these are going to be major hurdles. But when we're doing chemistry in an academic setting, it's very challenging. It's nice to know if we have a break, it might have some impact. And furthermore, it's a lot of fun to work on these projects, and so we've been having a great time doing this, and the projects are really well suited to an academic setting at this stage. So I should stop and thank people. I mentioned Jay early on. Jay is a faculty associate at Caltech, and he works a lot with my group, also with some other groups at Caltech. And much of the work I talked about, essentially all the work I talked about this afternoon, was done in collaboration with Jay's leadership. And we had a whole bunch of people working on this, as you can see. Started out as a little crazy idea we had, where we got some money from a so-called Caltech consortium of companies to try. And then DARPA took over of all people for a while. They dropped us. Texaco supported it briefly. The DOD, ARO looked at it. AxoNobel funded it for a while. And then NSF picked it up until BP came to us in around 2000 and said, after they read some of our earlier papers, how'd you like to be part of a methane conversion consortium? And we said, how much? And they said, how much? And we said, well, yeah, we'd like to be part of a consortium. And we worked in this area. Actually, Jeff started out working early on in this area. And it involves a collaboration between chemical engineers at Berkeley, Caltech chemists, mainly Oliver Angus is a chemical engineer, and BP scientists. It was called the Methane Conversion Cooperative. We had reviews twice a year, once at Caltech or Berkeley and once at a BP site. We all got together and talked about what we'd done and what we planned to do. And here we are at Caltech. Yeah, look at Jay. Jay, I wanted to point out Jay. Jay's actually smiling in that picture. If you know Jay, that's a rare event. He's a very dour sort of character, but I think it's and then later, when we switched to other kinds of substrates and methane, we renamed ourselves a conversion cooperative where X goes in place of M. You name X and we'll convert it. And so I think BP, they've been an absolute amazing patient and inspirational company to work with. As compared to all the others I worked with, they're really quite loyal and support you at a level where you can really do something. You can see here that this work is continuing. I'll tell you a little bit about what Aaron Sattler is doing tomorrow, where we take alkenes and selectively trimerize them. BP's very interested in that strategy as well. Here's some pictures of the group going back. Here's 2008, 2010, 2013. There's Dave Leach. He's now working at GlaxoSmithKline. And you can see the group has gone along pretty much the same size, and theirs getting a little smaller. And there it is last year. I haven't, here's Aaron. I'll tell you about it in the bar. There's Dave Leach as well. So the group is smaller, but I hope you enjoyed hearing about what they did when they were larger. And thanks for your attention.
Okay, I'm sure that John would be happy to entertain questions for. Yeah.
In the tandem alkene-alkane chemistry at the end, since the tantalum catalyst and the iridium catalyst have different requirements for olefin concentration, would running these reactions in a flow system be helpful or not? I don't know much about flow chemistry, but it seems...
Yeah, I think you could engineer that to your advantage. I'm not an engineer either.
Okay.
But I think, yeah, sure, you could somehow engineer the flow reactor to have
more hexene in
more
this
hexene
part.
and,
Yeah.
and put your catalyst in there physically at different locations.
Right.
But you do have to eventually get the alkene product out and back around, so you'd have to have some sort of a loop
Yeah.
catalyst in there, catalytic setup. But those, you know,
That's
chemical engineers
feasible.
talk about that.
Yeah.
So they can do that.
Have you looked at bifunctional nanoparticles? Because you said that the big problem is the cooperative. That both catalysts get along with each other, right? So if you would immobilize two catalysts on a surface, you know, keep them apart, you have a quasi-heterogeneous catalysis system, and you will completely surpass that problem, or?
Yeah, that's a good idea. In this case, it's not that the catalysts react with each other. If they were reacting with each other, your strategy would have a bigger advantage. You
Yeah.
still have the same issues with temperature and olefin concentration. But you could support them and hope that, you
Yeah,
can
I
separate
already
it
know
crazy.
about this ruthenium, iridium hydride systems.
Those things have been supported. Brookhart has described strategies for attaching that principally and directly to a silica support. So that can be done, and we've done some of that in our work with Mark Davis. I'll tell you that our initial experiments supporting both, that show that these things are just not reactive enough to, I mean, you talk about flow reactors, but there has to be a finite flow. And so when the reaction rates get slow enough, it's really hard to see enough product in the form to really do anything meaningful that way so far. Maybe we'll find something that's more active.
Yeah, Rich?
The family of iridium catalysts that you were attempting in the hydrogenation chemistry side, and the limitations that you saw with the ordering olefin, wondering of that family, how many did you try, and they all have the same dependence on olefin order that way?
We did not look at a whole family. We only
You
looked
showed
at
COCOM,
the
you showed
T-shirt.
the tetrahydride.
Yeah, you're right, there's a lot of them. And they've been looked at mainly by Alan Goldman and Maurice Brookhart, and a lot of them have shown those same mechanistic features.
I see.
The olefin isomerization happens from the alkene adduct through an allyl hydride mechanism that's been convincingly shown. And that seems to be fairly general, that they like to sit in this alkene adduct form rather than in the hydride form when you have enough olefin around to shift that equilibrium over there. I think it's a general observation, but heck, never say always. You might find a system where that's not true.
So I have two kind of big picture questions. One, you talked a lot at the beginning about CH activation, partial oxidation, and then you went through this nice study of the platinum chemistry. Do you think if you wanted to study CH activation, are oxidative, autocatalytic processes even worth studying if you want to do them for this purpose? And if not, is the platinum chemistry worth revisiting with other systems or other ideas? I kind of wanted your perspective on that, since it seems like...
You mean, let me get the first part. So, you mean auto-oxidation? Is it
Right,
both
so-
this?
yeah,
That's more or less
exactly.
what you're saying. And if you ask Jay Lebinger, he would say yes. In fact, he's
In fact,
famous for
probably.
his Lebinger limit. And that is that no matter how you engineer it and so forth, including this slurry setup that I mentioned briefly, if you involve radical intermediates in the gas phase, I guess he would exclude the possibility that you could somehow use occlusion or some sort of steric thing to change the relative rates. But at least in the gas phase, you're never going to beat about 5% per yield per pass without making prohibitive amount of over-oxidation products because the products are simply more reactive than the starting material. That's the whole bottom line. And occasionally over the last 20 years or so, there have been reports in the literature that exceed the Lebinger limit, and by a large fraction in some cases. And then people, of course, if that's true, they go back and try to reproduce that. And in every case so far, those have been somehow wrong. It's calculated or it didn't compensate for these other products that we're making and so forth. So I think it's pretty much hopeless. But the Schwab chemistry with palladium-2 we're revisiting. We think that has hope. But it's really hard to do. Palladium is wonderful because the palladium-2 goes to palladium-0 instead of platinum-4 to platinum-2. So it's a different redox couple. And if you capture the palladium-0 product quickly enough with dioxygen, it goes right back. And so there's a lot of catalytic oxidations involving palladium that use dioxygen directly without even copper around. It's not like the whacker chemistry all the time. It really doesn't work. It's fraught with, we're doing some of that. It's fraught with this platinum-0 formation to make nanoparticles that do the chemistry you think your ligated palladium-2 is doing. This palladium-0 is really pretty reactive stuff, it turns out. So we have that problem there. But we're seeing some things that would give me opportunity to activate certain kinds of CH bonds using that chemistry directly with dioxygen, without oxidation kicking in. So I think there is a place for that kind of chemistry. And people like Shannon Stahl are saying some pretty interesting oxidations that involve direct oxidation with dioxygen using palladium catalysts. So I have hope there.
So, Jim.
So your model system for the Shelob chemistry is a cationic platinum complex. And I'm curious, so if you go back to the original Shelob system, do you think that's also a cationic complex that activates methane? So could you have a disproportionation of the dichloride to a trichloride and a cationic platinum chloride?
I think, I showed it as a neutral, because that's what Alex Shalov liked, and I don't have any way to rule it out. But I think it could easily be a triacylchlorocation. I think that would help it be a stronger electrophile. People have, I have a lot of trouble thinking of platinum-2 as being able to coordinate a CH bond. I mean, come on. I mean, that's not the world's greatest electrophile. But I think it has to do with a sort of hard-soft concept, that if you put all hard ligands on platinum and it sees a CH bond, it sees it as soft liquid file that, okay, I'll take a little bit of it. And I think that's sort of how it thinks. If you didn't have this hard ligand set on it, or make it cationic on purpose, I think it wouldn't be reactive. Yeah, the tetrachloroplatinate is totally dead. So if you had lots of chloride, no chemistry. If you make the tetraaqua, now it's a dicatonate, people have made it, it's not very stable, and it decomposes before it reacts. So I think that's its problem. But I think the triaqua would do that.
So if you take the dichloro and you add something like silver salt to extract chloride, is that?
That's how people made the tetraaqua, was possibly doing that. But it doesn't want to give all the chlorides up, and so it's a mess. I mean, it's not like it makes it more active. These things disproportionate, and even though you think you've got triacylchloro, it may not be the major species in there.
Okay, with that, let's thank Professor Berger.